I'd like to discuss now, when we get the slide, examples of unique spectra that we have observed. Okay. This is an earlier flight we had in 1970. And could you focus it now? Can we focus, please?
Focus, Roger. Focus, please. You have to call when you want them now.
Okay.
Your slides are too fat.
All right. The middle panel here is the field-aligned current, again calculated for this flight. And the 4 all-sky camera pictures on top, I don't know if you can see it or not, at 110 seconds, the rocket is located here. And from up to about 190 seconds, we were conjugate to the aurora forum and then passed north of the aurora forum. And so here's the field-aligned current. There are 3 things I want to point out. First of all, this increase in field-aligned current here occurred, and you can't see it very well from these pictures, when a bright aurora forum or a small curl moved under the rocket position. This is the contribution to this current is a function of energy here, and it was when we're conjugate to the aurora, the major current was carried by 3 to 6 kilovolt electrons. Now here is the edge of the visible aurora, as we could determine from the all-sky camera pictures, but yet there's an order of magnitude increase in current just as we go past the northern edge. And it goes up to something like 5 or 6 microamps per meter squared. And if this is purely a spatial variation, this amounts to about 10 kilometers. And so it fits quite well with Jim Armstrong's one case where the current is at the poleward edge of the visible aurora. Now the third thing I want to point out in this slide is that when we were well north of the current sheet, the current actually on several occasions here reversed directions. And I'll show a little bit more of that in just a minute. Going back to this current sheet, this panel here shows the contribution to this current and was carried by very low energy electrons, a very enhanced flux of low energy electrons. There was no field alignment, however, during this time here. Field alignment occurred right in here, and I'll show that in just a minute. Could I have the next slide? This is the time when we saw the current actually reverse. I plot here the reflection coefficient, that is the ratio of electrons we observe going up the field line to the ratio of electrons we observe coming down the field line. So the edge of the aurora was about here, 190 seconds, and the ratio was 1 or less than 1, meaning there was more going into the atmosphere. But when we got north of the current sheet, then we see, for very short durations here, reflection coefficients becoming as high as 5, meaning that there is, for these 100 EV electrons, more going up the field line than down. This is a suggestion of perhaps we might be seeing the high energy tail of some return current pattern. The next slide this 6 spectra here, electron spectra, taken when we were above this bright curl which we went over. The pitch angle is given by the smooth curve, and it goes from the first 2 decades here, which goes from 1 degree to 100 degree pitch angle. So you see we see multiply peak spectra. There is one peak in the spectrum here which is isotropic in pitch angle. That is, no matter what pitch angle we're looking at, up to the maximum of 50 or 60 degrees, we see the peak. However, we see the second peak here only when we're looking at very small pitch angles. And so this peak here is a field-aligned peak, and it occurred during this time for approximately 20 or 30 seconds during the flight. The next slide is another flight, a third flight. This was an Air Force Cambridge Black Brant flight in which we had the similar detectors aboard. And I plot here 3 pitch angle distributions. The top one is 3.3 keV, the middle one is 4.8 keV, and the bottom one is 5.6 keV. So here are 3 pitch angle distributions. The 4.8 keV, as you can see here, is very sharply field aligned, whereas the other two, 3.3 and 5.6, are not field aligned. So here's an example of field aligned fluxes, which are also very monoenergetic. The next slide, please. Here's a pitch angle sorted spectra. Could you focus it, please? The solid curve is a 0 to 10 degree sort. That is the spectrum you get looking in the range of from 0 to 10 degree pitch angle. The other curves, which are not drawn in, the circles and dots, are the 30 to 40 degree sort and the 50 to 60 degree sort. Now, first of all, I want to point out that here is the very monoenergetic peak, which is field aligned. And you go to higher energies, you go to higher pitch angles, the peak in the spectrum moves to higher energies. And Dave Evans has been working with a model involving acceleration by parallel electric fields, which you'll talk about shortly. And he has fit these data quite well with his model. And his model requires, of course, that the peak in the spectrum move to higher energies as you go to larger pitch angles. I might just add, with regard to these data, that this flight was, these field-aligned fluxes were observed between two auroral forms. Okay, the next slide, please. Going back to our most recent flight in which we had field-aligned fluxes at the edges of the auroral arc. This is spectra showing this. Again, the pitch angle is given by the smooth curve. And you can see that when we go through small pitch angles here, we get a spike in the spectrum. There is some indication of another peak which is fairly independent of pitch angle, but it doesn't show up very good at this particular time. For this flight, the field alignment was not monoenergetic, but the fluxes that were field aligned were from about 0.5 kilovolt to 3 kilovolts. And if I could have the next slide, please, in which we show for three energy channels, the flux versus time. Could you focus just a little bit? The pitch angle is indicated here on these flux enhancements if it is less than 30 degrees. So this is the entire duration of time, about 300 to 317 seconds when we saw field alignment. And you can see when we're at small pitch angles, we get the enhancement of fluxes. And it occurred over a range of energies. In fact, it went from about 0.5 kilovolt to about 3 kilovolts. Notice how abruptly, bang, it just suddenly stops and there's no more field alignment. Okay, well, I'd just like to summarize these measurements of the field-aligned fluxes. First of all, you have to be mindful of the statistics here. We have only 3 flights, but the following statements seem to apply to these data. Due to the pitch angle energy scan of the detector system, one cannot absolutely determine the temporal or spatial nature of these field-aligned bursts. The data can be interpreted in terms of variations as short as a fraction of a second to as long as 20 seconds. Secondly, the degree of field alignment is great. Usually enhanced fluxes are observed with pitch angles less than 20 or 30 degrees and at times less than 10 degrees. Third, the detectors measured the electron spectrum, as I mentioned, from a few eV to 15 keV. Field-aligned electrons were observed from a few hundredths of an eV to 5 keV. We have not observed them at higher energies, energies greater than 5. One flight observed the field-aligned electrons to be very monoenergetic, whereas another flight observed the field-aligned electrons over a range of energies, from a few hundred eV again to a few keV. Spatially, the field-aligned fluxes are more often observed at borders of auroral displays. This is a region, however, where the auroral spectrum is changing rapidly, hence the change in the spectrum might be the dominant relationship. Finally, field-aligned fluxes have an uncertain relationship to the characteristic monoenergetic peak, usually seen above the auroral spectrum, in the auroral spectrum, and which we have observed to be isotropic in pitch angle. In 2 flights, the field-aligned fluxes occurred simultaneously with this field-aligned or this isotropic peak, but were quite distinct in energy. The occurrence of the field-aligned fluxes along with the isotropic peak results in multiply peak spectra. Okay.
Roger, I'd like to ask you something about the paper you published about, 6 months ago. It appeared in the same issue that paper by Chappell and myself did. And you showed there a case of a spectrum with the main, quote, monoenergetic peak at about 8 to 10 kilovolts. And then there was one case with a smaller peak at around 1 or 2 kilovolts. And I don't remember the pitch angle range. Was this, in that case, was that small peak around 1 to 2 kilovolts, was that also field aligned?
Yes.
Or was?
Yes.
Okay.
Usually when you got 2 peaks, as we see them, one is field aligned and the other is isotropic.
And is it true that the higher energy peak is isotropic and the lower energy
in
one
all of our cases, yes.
is field aligned? In all the cases?
The lower energy one is a field aligned one.
Okay. Thank you.
Did I hear you say that at real low energies you don't see field aligned?
Well,
I mean, from a few EV to a few hundred EV, you said?
yes,
No?
in the cases we have, the lowest energy at field line that we see is a half a kilovolt.
I don't want to quote somebody else's work because I don't remember it too well, but recent rocket flight by Hayes and Sharp, where their instrument measured from a fraction of an EV up to 500 EV, they saw field-aligned electrons in the tens of EV. So that's why I just checked.
We did go down to a few EV.
But in your case, you did not see
We
it.
did not. That's right. But it varies enough that it doesn't surprise me.
You don't see thermal electrons. You can't detect them.
No, just
So-
down to,
So
well,
can you exclude the possibility that there are equal and opposite currents carried by thermal electrons so that there's really no net field line current at all? I mean,
Well,
can you exclude that?
except for less than a few hundred EV, the electrons we do measure down to a few tens of EV or a few EV, those fluxes are usually isotropic. So there's no current carried by that group of electrons. So I don't know what happens to the thermal.